Alright, so this is part 2 to an introduction to logarithms, and in this part we're going to be focused mostly on graphing. So if you look at number 30, it says graph f of x equals 2 to the x power and its inverse on the grid. So the way that we graphed exponential functions is we made a little table. Now first I'm going to write f of x as y, so y equals 2 to the x. And when we make our table, we're going to let x be negative 1, 0, and 1. Remember, we said 2 to the 0 power is 1. The point 0, 1 is like our key point for this type of function. And then we want a point on either side of that. So we choose x to be negative 1, 0, and 1. So 2 to the 0 power is 1. 2 to the first power, if we plug in 1 for x, y will equal 2 to the first, which is 2. And 2 to the negative 1 power will be, let's see, 1 over 2 or to the first, or just 1/2. Now the thing that you'll find with these is these are always going to be reciprocals. And that's one of the nice things about graphing logs or exponential functions. We're going to have that in every case where we do the graph. All right, so let's go ahead and graph that. And we also learned that the asymptote is a key feature here. It's y equals 0, the x-axis basically. And so our graph's going to look like that. Now how are we going to graph the inverse? Well, one of the things we learned previously, because we didn't even have to find the inverse yet, we're just actually graphing it, is we can flip our x and y values of our points and get points that are on the graph of the inverse. So for the inverse, our table is going to look like this. And so let's go ahead. All I did was switch the x's and the y values. And so we're going to go ahead and plot these points. Now notice I've graphed y equals x. We learned that when you graph an inverse and or function and its inverse, there's going to be symmetry through this line y equals x. And so that's useful when you draw the graph. You're going to have 3 points, but the symmetry will help you to draw the graph because you should have symmetry through this line. So let's go ahead and graph these points, and you can see that the shape is going to look something like this. Notice I've got the vertical asymptote that I'm going to need, and the graph's going to look like that. So notice you can see the symmetry I was talking about. And so that's what our graph looks like for the inverse. So now what's the domain and range of f? That was our original function, y equals 2 to the x, the one that's graphed in purple here. So the domain there is all real numbers, which is true for any of our exponential functions. And the range is going to, let's see, we don't quite get to 0. We start from just above 0 and it goes up forever. So 0 to infinity would be your range. And now we could do the same thing with the orange graph, but we learned previously with inverses that we just need to flip the domains and ranges here. So the domain of f becomes the range of the inverse, and the range of f becomes the domain of the inverse. Now it says find the inverse of f of x equals 2 to the x using the 4 steps. So we've graphed the inverse, but we actually haven't found what it is. So let's go ahead and do that right now. The first step is to change, in fact, 2 of the steps are all about notation. First step is to change notation to the y notation. So we have y equals 2 to the x. And then the key 2 steps are the next 2. First, we switch our x and our y, and now we have to solve for y. So switch your x and y, and then solve for y. Now, notice we have the variable y in the exponent. This is the case where we're going to use the inverse function, which is the logarithmic function. All we need to do is change this to log form. So it'll be log base 2 of x equals y. So again, you can already see how important it is to be able to go back and forth between exponential form and logarithmic form. So notice by changing to logarithmic form, we've now solved for y, which was our exponent. And in fact, now we can write this using inverse notation. And so this is saying that the inverse of y equals 2 to the x is the log base 2 of x. In fact, if I had like y equals 3 to the x, then the inverse would be y equals the log base 3 of x. So really the only thing that changes is the base. So I want you to remember the inverse of the exponential function is the logarithmic function, and basically whatever the base is for the exponential function, that's going to be the base of the logarithmic function. All right, let's go ahead and move on. So here's a summary of what we talked about when we were graphing exponential functions, and now we're looking at log functions. Notice our base is still greater than 0 and not equal to 1. And it tells you the 3 points that we're going to use, and I'll show you those when we do our graphs. Notice, just like the graph we just did, our domain for the logarithmic function is 0 to infinity, and the range is all real numbers. When we were graphing exponential functions, we had a horizontal asymptote. When we're graphing log functions, we're going to have a vertical asymptote. And the only other thing I would add is right here, if the base is greater than 1, which it normally is, then our graph is going to have this basic shape where it's going to go through 1, 0, and it's going to look something like that with an asymptote that's vertical. So this is the most common graph that we're going to be dealing with when we're graphing logarithms. Notice our key point is 1, 0, whereas when we were graphing exponential functions, it was 0, 1. And again, this is when our base is greater than 0, or I'm sorry, greater than 1. If it were between 0 and 1, it would actually go the opposite direction. But we don't see that one as much as we'll see when our base is greater than 1. Let's go ahead and move on to do some graphs. So on the first one, it says f of x equals log base 3 of x. Let's use the y notation, and we're going to change forms. It's kind of difficult, or it can be difficult, to draw a table for a graph when it's in log form. You can certainly try it, but you got to be careful how you choose your x values. It's much easier to change this to the exponential form, which would be 3 to the y power equals x. Remember, it's our base to the y power equals x. So this is 3 to the y power equals x. Let's go ahead and make a table. Now notice this time I picked my y values to be negative 1, 0, and 1 because that's my exponent, the y is. So it's a little bit backward this way, but notice if I put a 0 in for y, 3 to the 0 equals x. Well, 3 to 0 is 1. And if I plug in 1 for y, 3 to the 1 power would equal x. Well, that would be 3. Now I can plug in negative 1 and you get 1/3, but I always just think I'm going to get the reciprocal of what I had here, and so it's going to be 1/3. So these two numbers are always going to be reciprocals. All right, so let's go ahead and plot these points. And we know we're going to have a vertical asymptote at x equals 0. And let's go ahead and draw the graph. And so it looks like that. Now look at example 2. Our parent, oops, I'm sorry, I got to do domain and range here. Notice the domain here is 0 to infinity, which is true with all of our basic log functions where we haven't done any kind of shift yet. Our range is all real numbers. All right, so on number 2, our parent function is going to be y equals log base 3 of x, which we just graphed. And so the only difference here is because the minus 2 is inside with the x here, we're going to have a horizontal shift. This is the one that works kind of opposite or backwards. So we're going to go right 2. So let's go ahead and graph the log base 3 of x, our parent function, and then we need to move all of our points right to. Now notice if we move the graph right to, our asymptote is all the points on the asymptote are also going to move right to. So let's go ahead and put in our asymptote. It's going to be x equals 2, and there's our graph. So I just moved each point right to, and that included the asymptote as well. So notice here our domain is changing because everything moved 2 to the right. It's going to be 2 to infinity, but our range is still the same, all real numbers. So be careful how you draw this part. It's important that it goes up, even though it's going kind of up slowly, because your domain, or I'm sorry, your range will be all real numbers. It does go up forever. It's important that you can see that in your graph. All right, let's move on to number 3. So here our parent function is the common log. Y equals the log base 10 of x, or the log of x. And so let's go ahead and make a table. But first we want to go ahead and change to exponential form. Our base is 10, the exponent is y, and the answer is x. And we want to make a table where the y values are -1, 0, and 1. So when we plug in 0, we're going to get 1. 10 to the 0 power is 1. When we plug in 1 for y, x will equal 10 to the first power, which is 10. And we know this other value will be the reciprocal of 10. Let's go ahead and plot those points and put in our asymptote. So now, if you look at the -2, notice that's totally separate from the log of x. We sometimes would see it after the log of x, but notice it came first here. But it's going to cause a vertical shift, and that's going to make things go down 2. So we want to move our points down 2. Notice that's not going to affect our asymptote at all if we're moving the graph down 2. So your graph's going to look about like that. You got to move each of your points down 2, and then just draw the graph. It's not easy to draw that going off to the right, and again, you want to make it look like it's moving up, because it is. It can be a challenge. You can see I didn't do so great here. So our domain, 0 to infinity, and our range is all real numbers. Again, you can see it's important that you make that look like it's going up so that you don't mess up the domain. Let's look at example 4 here. So here our parent's going to be the natural log. So that's base e. So if we're going to change forms, it'll be e, our base e, to the y power equals x. And so now let's make a table. Again, our y values are -1, 0, and 1. And if we plug in 0, e to the 0 power, we're going to get x equals 1. If we let y equal 1, x will be e to the 1 power, which is just e, which is about 2.7. Now remember, you can do second ln on your calculator to pull up e, and just put in a power of 1. Now the reciprocal of that is 1 over e, and if you do that on your calculator, you get about 0.4. So make sure you can get that value, 0.4. So I'm going to go ahead and graph the parent. And now we need to look at what we need to change here. So notice the minus out in front. That's going to cause, oh, you know what? I think I made a mistake on this one here, because that's not right. This is going to go through the, be reflected through the x-axis. So I think I need to fix this. Hold on just a second here. The +3 there is going to cause us to go left 3. I need to fix this though. Let me go ahead and I need to erase this stuff here. So let me go back and do that. All right, so we actually need to reflect this through the x-axis. So this point here is not going to move. Oops, let me change colors. So the point on the x-axis is not going to move. 2.71, that's going to go down here. And 0.4, negative 1 is going to go up here. So this is, let me finish drawing this here. This is y equals minus ln of x. Now we got to move everything left 3. So let me change colors here. So if we're going to go left 3, that will make our vertical asymptote move left 3 as well. And let's move each of these 3 gray points left 3. So 1, 0 is going to go 1, 2, 3. It'll be right there. And we need to move 0.41. Let's see, 1, 2, 3. So about right there. And I've got to move this third point. 2.7, negative 1. Let's see, 1, 2, 3. So it'll be about right there. So the graph's going to look something like that. All right. So our domain for this graph is going to be negative infinity. Oh goodness, I messed that up. Let's fix that. Actually, it is negative 3 to infinity, isn't it? No, I just wrote it backwards. So it's negative 3. Whoops, let me change colors. Negative 3 to infinity. And then our range. Now there is no lowest point. It does keep going down forever and it does go up forever. So it is all real numbers. All right, let's move on to example 5. So it says determine the domain of f of x is equal to log base 3 of x minus 2. Now, in this case, all we have is the equation of this function. So let's look at the graph of the log base 3 of x. We actually did this earlier. It looks like this. And notice it goes to the point 1, 0. We have an asymptote at x equals 0. But the thing I want to look at is the domain. Notice the domain is 0 to infinity, which is what we said earlier. Which means, remember, the domain is the set of all the x values. So what we're really saying is if you look at all the points on this graph, the x values go from above 0, not quite as low as 0, to infinity. Another way to say that is x is greater than 0. So if you look at what we have here, log base 3 of x, our x value has to be greater than 0, which means we cannot take the log of 0, and we cannot take the log of a negative. We can only take the log of a positive number. And so what we're going to do is we're going to take the x minus 2 there, the thing that we're taking log base 3 of that number. That number cannot be 0, it cannot be negative. The value of that has to be greater than 0. So if we solve this for x, we get x is greater than 2. In interval notation, that would be 2 to infinity. So notice if we actually plugged in 2, the log base 3 of 2 minus 2 would be the log base 3 of 0. You can try it in your calculator. Actually, you won't be able to do that yet. You could do the log of 0 on your calculator or the natural log of 0, and you see that you get an error message. You cannot take the log of 0 or a negative number. Notice if I plug in something that's not in the domain, like 1, then the log base 3 of 1 minus 2 would be the log base 3 of negative 1. Again, we can't take the log of a negative. You could also try that with the common log of -1 and you get an error message. We can never take the logarithm of 0 or a negative number. So that's how you find the domain. So look at number 6. We need 5 minus x to be greater than 0. So we're going to subtract 5 on both sides and divide by -1. Now remember, when you do that, division by a negative with inequalities, you've got to reverse the symbol. And so we're going to get x is less than 5. And so if you write that in interval notation, it looks like this, -infinity to 5. And again, I just want to point out that as long as you choose a value from -infinity to 5, not including 5, you can take the log of those numbers. But if you plug in something that's not in that domain, then you'll get an error message. Again, that's because you can't take the log of 0 or a negative number. All right, let's look at our last problem, example 7 here. It says write the equation in exponential form and then solve for x. So here we have 5 to the second power equals x plus 4. And 5 squared is 25. We'll subtract 4 on both sides and we get 21. So x equals 21 is the solution there. And if you actually plug it in, it will be the log base 5 of 25 equals 2, which is correct. Let's look at b. It's 5 to the -2 power equals x. Again, you can see why it's so important that you can switch back and forth between the two forms. And that's just going to be 1/25. So that's the end of this video.